So this is the final exam of MIE 100 from 2024. So again, this course is there are a lot of concepts in the course. So from chapter 2 all the way to chapter 8, we cover a lot of things. And just so we're on the same page, and eventually we'll change books, of course. This is Engineering Mechanics Dynamics, 9th edition from Wiley and Son. And we're covering particle kinetics, kinematics, rigid body kinematics, rigid body momentum, energy, and vibration. So the entire text, everything that's been covered in lectures from the beginning of term to the end. Problem 1, the system is at rest with the spring unstretched at theta equals 0 degrees. The 7-kilogram uniform bar is given a slight clockwise nudge. If the bar comes to a momentary stop when theta is equal to 70 degrees, determine the spring constant k. For the value of k calculated, determine the x and y components of the centroid's velocity vector when theta equals 50 degrees. And theta is shown on the figure. So you really have to read through the problem and look at the figures very carefully. When theta equals 0 degrees, the chord length between A prime and the upper pulley is going to be A prime to B, and then it's A to B. L naught then is 0.13 meters. For theta equals 70 degrees, AB is given by the Coase law, and you can calculate that out to 0.77 meters. Therefore, the spring is stretched by a total distance of 0.64 meters, 0.77 minus 0.13 meters. And this is a chapter 6 problem. You set the datum at 0, so the bottom, that's where the green line is, T1 plus V1 plus work 1 to 2, T2 plus V2. This is the conservative form. And you put in the terms that you have, height at the beginning because the system starts at rest, height at the end, and 1/2 k delta squared. So putting all the terms in, calculating everything, and the spring stretch, you end up with k, which is twice the weight divided by delta squared over h1 minus h2. Or k carried out to a ridiculous number of decimal points, 66.1343 newtons per meter. Using that value, you then can calculate for theta equals 50 degrees, what the length of the cable is. So, or what the stretch is, it's going to be 0.574 minus that L naught, 0.44 meters. T1 plus V1 equals T2 plus V2. Now the difference here is T2 is not 0, and so there's a 1/2 mv squared term. H1 is 0.6 divided by 2 meters, 0.3 meters. H2 is H1 divided by times cos theta, which is 0.13 meters. I is, it's a pin rod at an end, 1/3 m times the distance OA, and it's 0.84 kilogram meters. Putting all the terms in, calculating everything out to the end, you end up with VG, which is going to be the distance OA divided by 2 times omega. You've calculated, or you would have found, omega from the previous part, which is 1.405 meters per second, and it ends up being, rads per second, 0.422 meters per second. That's probably, again, when you're doing your calculations, it's helpful to carry them out to 4, 5, 6 decimal places. When you write them, you're really only expected to do 2. Velocity of the center of mass, then, putting in all the terms, looking at the distances, is just, and breaking it up into its components, it's 0.4 cos 50I minus 0.4 cos, or sine 50J, 0.4, it's 0.4221, minus 1.4 rads per second. So clockwise rotation, and there you go. Arm AB has a constant angular velocity of 150 RPM clockwise when at the instant when theta is equal to 31 degrees, find velocity of point D and acceleration of point D. So you're given a bunch of distances, 10 centimeters A to B, 35 centimeters B to D, height of 20 centimeters, and theta, which you're given in the problem, G is acting downward, and you're given the positive XY and positive rotation. So beta in that diagram is just going to be ADY minus ABY divided by BD, and in that case, you end up with 25.11 degrees. Put all the terms in, get the directions. Velocity of B is normal to the link AB. And you can solve it vectorially, and you get minus 0.08 or 0.81 I 1.35 J meters per second. Split it into components for velocity of D with the reference velocity B plus omega BD crossed with RD with respect to B, and you end up with two equations and two unknowns, velocity of D and omega BD. And from that, you get velocity of D, which is equal to negative 0.1782 meters per second in the I direction, which makes sense, and minus 0.425 rads per second K. Acceleration of point D, same thing, acceleration of D is equal to acceleration of B minus omega BD squared RdB plus alpha BD cross with RdB. Put in the terms, you've got everything except acceleration B, you got everything you need, you have unknowns, alpha BD and acceleration D, two equations, two unknowns substituted. You're not asked for this, but if you're bored and you want to try this on your own, you can also calculate the acceleration of G of that link, and that is going to be 27.615. So this is AG of the link BD minus 27.615 meters per second I minus 6.35 meters per second squared J. String of mass, zero mass, length 3 meters is tied at one end to a small sphere of mass 0.4 kilos. The other end of the spring is tied to the origin O. The sphere is moving around the origin in a vertical plane as shown in the diagram. Assume air resistance and friction are zero. At the instant shown in the diagram, the angle is equal to theta equals 60 degrees. All that's shown on the figure. Speed of the sphere is 8 meters per second. The angle theta is measured counterclockwise from the x-axis as shown in the diagram. Determine the y component of the acceleration of the sphere at that instant and find the velocity of the sphere in xy coordinates when theta equals 200 degrees. So lots of things going on, but basically it's just essentially a kid sitting in the center and a ball and a spring or a string attached to that ball, and you're just sort of rotating around. So if you look at a free body diagram of that, you have an accelerator or a tension which is acting down towards the center of rotation. You have weight which is acting down, and the tension is acting with 60 degrees with regards to the horizontal. So with that free body diagram, you can immediately write an equation for the normal force, T plus mg sine 60 equals mv squared r. Put all the terms in, you can calculate T, and you get 5.13 newtons. If you go with the force in the y direction, now that you know what the tension is in the cable, you can substitute in all the terms. You can find the acceleration in the y direction, and it's minus 20.93 meters per second squared. It kind of makes sense. It's going towards the top of its swing. It's probably going to be acting or slowing down. Find the velocity of the sphere in xy coordinates when theta equals 200 degrees. So it's rotating. There's nothing that's really taking energy out of this system. It's a conserved system. You have an initial velocity, and then you have a change in potential. Now, two ways to do this. You could write T2 plus V2 equals T1 plus work 1 to, or T1 plus V1. Or you could write it this way, and honestly, I should have written it as T1 plus V1 equals T2 plus V2. Either way, I end up with the same equation. So you can see 1/2 mv1 squared plus mgh1 equals 1/2 mv2 squared plus mgh2, and I brought it over to the right-hand side. You have h1, h2 at the two distances, so you know that it's going to have two different heights. It's going to be towards the bottom of the swing, and delta H is 3.63 meters. Substitute in all the terms, you get V2 squared equals V1 squared plus twice G times the distance change in height. And substituting everything in, you get V2 equals 11.62 cos 70 minus sine 70 in the I and j directions, respectively, which kind of makes sense when you look at the diagram, and that's one of the reasons why you would draw the diagram. So you have a positive I direction and a negative j direction, which is really what's being shown in that blue line that you see at the bottom. Problem 4 was a momentum problem. In a horizontal plane, two slender bars are attached to each other through the center and at a 90-degree angle. They can freely rotate about point O. Mass A equals mass B. Mass AB equals mass CD of 2 kilograms. Length AB equals length CD, which equals 3 meters. When T equals 0, the two-bar systems rest, and then a bullet with mass of 0.04 kilos and velocity of 200 meters per second hit at point A. What is the radius of gyration for the two-bar system around O before impact? During impact, determine if any of the following is conserved. Use yes if conserved and no if not conserved. After impact, the bullet will remain in the bar and they will move together. Find the final angular velocity of the system. Radius of gyration for any type of system is a compound body. So for AB, it's 1/12 ml AB LAB squared. Put the terms in. IAB about O, ICD about O are exactly the same. You add them up and you end up with 3/2 kilogram meters squared. After that, you can add them together because that's what you do, and you end up with I equals 3 kilogram meters squared for the system. And I equals 3 kilograms is equal to mk squared. So mass of the system is 4 kilograms. K is the unknown. 3 is what you're given. And you end up with K, which is equal to 0.87 meters. During impact, determine if the following are conserved. Kinetic energy, no. Linear momentum, no. Angular momentum, yes. We never talk about elastic and plastic collisions in the course. So we can say in collisions, kinetic energy is not preserved. Energy is lost to heat. Additionally, if one object is fixed, like a joint connecting to the ground or ceiling, the reaction force from the attachment can cause total linear momentum not to be conserved. However, angular momentum can remain conserved if we consider it relative to the attachment point. Since the reaction force acts directly at that point, the moment arm distance between the point and force application is 0, and the reaction force doesn't contribute to the change in angular momentum. So using angular momentum, we say the initial and final are equal. We have the initial velocity of the system, which is 200 meters per second, put it in. And we have a moment arm, which is LAB over 2 sine of 45. Substitute it in, put all the terms together, and you end up that equal to the final angular velocity, angular momentum of the system, and you put everything together. Everything works out. You end up with omega equals 2.75 rods per second. So that's a scalar approach. Everything will work out. You could do R cross MV bullet. You'd find H1 is equal to 8.49 Newton meter seconds in the K direction. Substitute all that. It all works out the same way. You get the same numbers. Everything is good. Finally, we have the vibrations question. Every year we get a vibration question. This one went actually quite well. 2 uniform rods, each of mass 10 kilograms, length of 0.9 meters, are welded together to form the assembly shown. The assembly is pinned and free to rotate about point C. Knowing that the constant of each spring is 735 newtons per meter and the end day is given a small displacement and release, to draw the free body diagram. Now, what is the natural frequency of the system? So you're given a lot of information. You're given positive X and Y, G acting downward. Mass of the rods are the same, 10 kilograms. K of the spring equals 735 newtons per meter, and the length of the 2 rods exactly the same again, 0.9 meters. So you're asked first part of the problem is to draw the free body diagram. This is all from chapter 6 and 8. You have the forces from the spring, which are acting to cause a moment. And this is important. In this problem, we have rotation. And so we're going to solve it using sums of moments, not sums of forces. And then we have the 2 weight forces. mass ACG, mass CB or BDG, and the reaction forces at the pin AXAY. Those are all the forces you needed to consider. If you wanted to, you could combine by showing clearly that you have done this combination by adding the two forces and then finding the centroid of the system, which is about 1/4 of the length of the vertical rod. Then out of that, you have the accelerations in the tangential and normal directions. You have the angular rotation, IG alpha of both. So if you recognize, first step was to recognize this was a moment problem. You cannot use a force balance for this. Sum of moments equals I effective times alpha. I effective is the same thing as we did in question 4. Substitute in all of the terms from your free body diagram, which you just did. You've got weight, you have the spring forces, and they all cause moments, and you've got to calculate them correctly. You have the moment forces, the moments of inertia and the mass, and you have to shift the mass from AC into point 2. And so you have L alpha, L squared, L over 2 alpha, L over 2 squared alpha for that term to replace the acceleration of the link AC. Putting all the terms together, putting in your eyes, calculating everything, and substituting everything in, you end up with an expression out of that. And that expression is just going to be 10/24 ml squared theta double dot plus KL squared over 2 minus MGL over 2 theta equals 0. So that's your governing equation. And when you rewrite it in the form that we recommend in lecture, you end up with this. The term in yellow, you solve the problem with that. You can put all of the terms in. You can write the expression. You end up with 75.12 rads squared per second squared. Square root it, 8.66 rads per second. And Fn, which is omega n divided by 2 pi of 1.38 hertz. One of those, natural circular frequency. The other, the natural frequency. I know that in our previous text we had a reversal in terms of how these were defined. It doesn't matter. You're required to know what they are, and this is one of the reasons we allow you to bring in a crib sheet. So, unlike the midterm, we pretty much fill everything in this dynamic concept inventory. Different points on a rigid body have different velocity and acceleration, which vary continuously. So 1, 2, 4, and 5. Rigid bodies have both translational and rotational kinetic energy, question 1. The only thing we missed was a wheel, a rolling without slip problem. And the other one is direction of friction force on rolling rigid bodies not related to fixed weight to the direction of rolling. We don't really talk about that too much. We do examples, and I often get questions on Piazza about it. And it's helpful to sort of think about this, and I know it causes a great deal of confusion. I can't stress it enough. I don't want to waste syllabus space by just putting the dynamic concept inventory. I think it's important. And the other thing is we're not very clever. We don't change things year by year. Look at past exams, and that coverage is going to be very similar to what you can expect each term.